and welcome to our video on section 5.4, Simplifying Rational Expressions. As you'll recall from section 6.2 red, we know that we can reduce fractions if we take out common factors. So when we think of 15, we know that it's 3 times 5, and 18 is 3 times 6. That allows us to cancel the common factor and thereby reduce the fraction to 5 over 6 in its simplified form. This process is what we will apply to rational expressions. And again, rational expressions are fractions that have variables in either the numerator, the denominator, or both. So let's go ahead and look at our first rational expression. What we want to do is put both the numerator and the denominator into factored form. So in the numerator, I'm going to factor out a GCF, and in the denominator, I'm going to factor the difference of squares. Now, what's going to be a little different here is that we are going to simplify, but we are also going to look for restrictions on the variable. And restrictions come from looking at the denominator and recognizing that we can't divide by 0. Therefore, anything that would make it 0 in the denominator has to be excluded or restricted from the domain. So let's get back to our simplifying. We can see that we have a common factor of x minus 2 in the numerator and the denominator, and we can therefore cancel that common factor, and we're left with our simplified form of x over x plus 2. That's our simplified answer, but we also want to consider the restrictions on the variable. In this case, we're going to look at the denominator and say, well, since it can't equal 0, we know that x plus 2 can't equal 0, and likewise, x minus 2 can't equal 0. So notice we're doing the restrictions before we've simplified. Here, when I solve, I get x cannot equal negative 2. And here, when I add 2 across the cannot equal sign, I'm going to get that x cannot equal positive 2. And we can clearly see that if we go back to the original expression, either positive 2 or negative 2 would make a 0 in the denominator, which would make the rational expression undefined. All right, moving on to our next example. In our next example, we have a negative exponent. And if you'll recall, a negative exponent means that we can rewrite it as a positive exponent by moving it below the fraction bar. So what I'm going to do is I'm going to write the numerator, p squared minus 4p minus 5, and then I'm going to move the p plus 1 that has the negative exponent below the fraction bar, and the exponent will become positive. Now I can go ahead and factor. So this is going to be p minus 5 times the quantity of p plus 1. And if I write the p plus 1 quantity squared in expanded form, it looks like this. So we have a common factor in the p plus 1 in the numerator and the denominator, which allows us to simplify the rational expression to p minus 5 over p plus 1. Don't be tempted to cancel out these p's, because remember, this is, again, we can't cancel unless we're in factored form and we have a perfect match. And now we can go ahead and do our restriction. And the order wouldn't matter if you wanted to do your restriction first, but I'm going to look at the factored form before I simplified, and I'm going to say p plus 1 cannot equal 0. Well, because it's the same factor, I'm not going to list it twice. I'm just going to say p cannot equal negative 1. Now, in the last unit, we talked about double roots and triple roots. When we give our restriction, we don't need to denote that it is a factor twice. So because we're excluding it, there's not the need to write the dr or anything like that. All right, so now let's look at our next rational expression. And we're going to go ahead, and our mantra in this unit is to always factor before we cancel. So I have the difference of squares, because remember, any even exponent is a perfect square. And then in the denominator, I have 4 terms, so I'm looking for a GCF and I don't see one. So I'm just going to use my factor by grouping skills to take out a common factor of t squared for the first term, and then I have plus 1 times the quantity of t plus 1. So then if I continue, what I have is I have another difference of squares in the numerator with t squared minus 1. So I can factor that to t plus 1 times the quantity of t minus 1. And in the denominator, I'm going to go ahead and look at this common binomial of t plus 1. I'm going to take that out, and I'm left with t squared plus 1, which cannot be factored further because it's the sum of perfect squares. So what I have here is a match in the numerator and the denominator with t squared plus 1. I also have a match with the binomial of t plus 1. So I'm going to be able to cancel the t plus 1's, and I'm also going to be able to cancel the t squared plus 1. So what I'm left with in simplified form is t minus 1. Now let's go ahead and look at our restrictions. So again, in factored form, the denominator is what we care about, and we know that t plus 1 cannot equal 0, and we know that t squared plus 1 cannot equal 0. So here we're going to get that t cannot equal negative 1, and here what we have is t squared cannot equal negative 1. Let's think about it. Anytime we square a number, whether it's positive or negative, it becomes positive. So this case can never exist, and we don't need to worry about solving for it. So the only restriction that we're going to list is that t cannot equal negative 1. In our next example, we see something that may look like the same in the numerator and the denominator, but they are not. So be careful here. In the numerator, we have the difference of squares, and in the denominator, we have a binomial taken to the 3rd power. These are not equivalent. So I'm going to use the factor pattern that we learned for the difference of cubes. I'm going to use 1 minus r because the cube root of 1 is 1 and the cube root of r to the 3rd is r. And then I'm going to use 1, opposite sign, 1 times r is r, always positive, r squared. So that's the factored form of my numerator. My denominator, though, is 1 minus r times the quantity of 1 minus r times the quantity of 1 minus r. So here we have a binomial match in the 1 minus r. We can cancel those once they're in factored form, and we're going to be left with 1 plus r squared over 1 minus r quantity squared. Now, if you wanted to, you could put that in standard form in the numerator. Remember that trinomial is not going to be factorable, and this would be our simplified answer. So when we go to do our restriction, we have 1 minus r cannot equal 0. And we have that 3 times, but remember we don't need to identify multiplicity in our restrictions. So if I just add r to the other side, I get that 1 cannot equal r or r cannot equal 1. So that is going to be the only restriction on this rational expression. Now we're going to look at a slightly different form for the next few questions that we'll see in the Green Book. We're going to give both the domain and the zeros of the function. So with the domain, we have been doing that by looking at the denominator, just as a reminder. And the zeros are the values that make the numerator equal to 0. So they are the values that make the numerator, if I could spell, that would help, numerator equal to 0. And we want to, the domain is going to restrict I'm just going to write that out. Restrict whatever makes the denominator 0. So a couple of important things. Here we're restricting and we're looking at the denominator. In the zeros, we are not restricting. We're giving the values that make the numerator equal to 0. So it's going to be done in a positive format. So in our first example, we have something already in factored form so that we can introduce this concept. And we're going to start with the domain. And in the domain, we're going to just look in the factored form and say 2x cannot equal 0, x plus 3 cannot equal 0, and x minus 3 cannot equal 0. So we're going to say that all reals except x cannot equal 0, negative 3 when we solve, oops, I forgot the 0 here, negative 3 or positive 3. That's going to be our domain. Our zeros come from setting the numerator equal to 0, and these are going to be given in a positive form. So notice I'm not putting the does not equal. So in this case, I'm going to get x equals negative 4 or x equals 1. These are going to be the zeros of the rational expression. Now that we've looked at one, I just want to go back and kind of write a note that might help. So in the domain, what we have is, if we have a fraction, say that it's 2 divided by 0, then the 0 in the denominator makes it undefined. Versus if we have 0 in the numerator, if we have 0 over 2, and I just picked 2 for simplicity's sake, but if we have 0 over 2, that's still going to be equal to 0. In other words, it's okay to have 0 in the numerator. Okay, so let's go ahead and look at our next example. And here we see that we have the sum of cubes and the sum of perfect squares. We can factor the numerator, but we can't factor the denominator. So as we've seen before, when we do the domain, if we have a squared term and it ends up being equal to a negative, then we're going to realize that that is not possible, and therefore there are no restrictions. So all real numbers would be the domain. And again, let me put domain at the top here with the A. When we do B, we're going to be doing the zeros of the function, and so we're going to set the numerator equal to 0. So we've got two factors in the numerator, x plus 3, and we've got x squared minus 3x plus 9. So for our purposes, we're just going to list one zero of x equals -3 because this trinomial is not factorable, so we don't include any zeros. And now we have our final example, and let's just go ahead, and I don't think one of these was shown in function notation. So if we wrote it in function notation, it would look like this. And when we ask for the here the domain and the zeros, this one is not in factored form, so that's the first thing we're going to do. We're going to factor out an x, which would leave us with 3x squared minus x minus 2. And in the denominator, I'm just going to write this in expanded form because it's already in factored form, but it's easier to actually see it when we have the x plus 1 written twice. So if I do the factor pairs of 3 and the factor pairs of 2 that have a difference of 1, I'm going to be able to factor to 3x plus 2 times the quantity of x minus 1. And what I'm going to find is that I only have let's see, let me make sure I did this right, minus 3, yeah. So I only have one term to cancel. I apologize, we're not simplifying these, we're just doing the domain and the range. So, I mean the domain and the zeros. So for part A, which is the domain, we're going to look to the denominator. So domain, denominator, I always think DD. So we're going to say x cannot equal 0, x plus 1 cannot equal 0, and we don't need to list that twice, even though it's a factor twice. So here we're going to have x cannot equal 0, or x cannot equal -1. So when we list our domain, we're going to say all real numbers except two values. There are two values that could make it 0 in the denominator. And then when we look at our zeros, again, let me show the factored form here. So when we look at our zeros, we're going to be looking to the numerator, and we're going to be thinking in positive terms what makes it 0 in the numerator. So I have three factors. I'm going to set each of them equal to 0 and solve. So the first one doesn't need solving. The second one, if I subtract 2 and divide by 3, I get -2/3. And then this one, if I add 1, I get 1. I'm just going to bring this down so they're all in the same line. And we could box that, or we could use our solution set notation to write 0, -2/3, and +1. So those are going to be the zeros. So that concludes our video on section 5.4, Simplifying Rational Expressions from the Green Book. So bring your questions to class, and I'll see you in the next video.